Hi, my name is Gillian Li, and today I'm going to be explaining the acid-catalyzed hydration mechanism for the addition of water to an alkene with a 1,2-methyl shift. To explain this mechanism, I'm going to be using the synthesis of 2,3-dimethyl-2-butanol from 3,3-dimethyl-1-butene as an example. Before we begin synthesizing 2,3-dimethyl-2-butanol, it's important to note that 3,3-dimethyl-1-butene, sulfuric acid, as well as 2,3-dimethyl-2-butanol are all hazardous chemicals. Because of this, we have to wear the proper PPE. Before I begin explaining the mechanism of this reaction, it's important to define a few key terms. The first term that needs to be defined is a nucleophile, which is an electron-rich species that has a pair of electrons it can share. On the other hand, electrophiles are electron-deficient species, and they look for a pair of electrons. Because nucleophiles want to share electrons and electrophiles want to have electrons, this causes nucleophiles and electrophiles to always react with each other. In the very first step of this reaction mechanism, the water and sulfuric acid they react together because the acid is the electrophile in the reaction while the water is a nucleophile. Because of this, the water, more specifically the oxygen lone pair, will act as the nucleophile and attack the electrophile. And by attacking the hydrogen in the electrophile, the oxygen will now form a new bond with that hydrogen. But since hydrogens can only have one bond formed, this causes the bond between the hydrogen and this oxygen to break, and those electrons will go to this oxygen. The second step of the reaction mechanism is having the hydronium ion that was formed react with 3,3-dimethyl-1-butene. In the reaction, 3,3-dimethyl-1-butene is the nucleophile because it has pi bonds that it can share with the electrophile, which in this case is the hydronium ion because of the positive charge on the oxygen. The oxygen also doesn't want to have this positive charge because it is a very electronegative atom and would rather have a neutral or negative formal charge. Because of this, the nucleophile will share its electrons and attack the hydrogen in the hydronium ion, which will cause the bond between hydrogen and oxygen to break and move those electrons to the oxygen, which will neutralize its formal charge. This step is the rate determining step because the addition of the electrophile to the alkene is a relatively slow process because the pi bond must be broken from the nucleophile. From this reaction, the addition of the hydrogen from the electrophile follows the Markovnikov addition, which is the addition of the hydrogen to the carbon that has more hydrogens attached to it, which in this case would be this carbon here. The next step of this reaction mechanism involves the 1,2-methyl shift. A methyl shift can occur whenever a more stable carbocation can be formed by moving an adjacent methyl group with its electrons from one carbon to the adjacent carbon that has the carbocation. In this case, there are methyl groups that are able to be moved in order to form a more stable carbocation. So this methyl group will move to where this carbocation is, and by having this 1,2-methyl shift occur, the carbocation is moved from a secondary carbocation to a tertiary carbocation. And a tertiary carbocation is more stable because carbocation stability is determined by how substituted that carbocation is, as the positive charge of the carbocation is able to be more spread out among the carbons that are substituted to it due to the hyperconjugation of adjacent carbon-hydrogen sigma bond electrons. Thus, by having a 1,2-methyl shift occur to form a tertiary carbocation, a more stable carbocation can form and is preferred for the reaction to occur. After the 1,2-methyl shift occurs, water, which is in the solution, acts as the nucleophile for the electrophile, which is the compound that has a carbocation, and the nucleophile attacks the electrophile where the positive charge is. Water acts as the nucleophile in this step rather than the hydrogen sulfate ion that was formed in the very first step of this reaction mechanism because water is more abundant in the solution to form the product we see here. The next step of this reaction mechanism involves water, again acting as the nucleophile, attacking the electrophile. Specifically, water will be attacking the hydrogen and oxygen with the positive charge so that the electrons in the hydrogen-oxygen bond become displaced and go to the oxygen with a positive charge. And this reaction causes the alcohol functional group to be formed, resulting in the end product of 2,3-dimethyl-2-butanol. No stereochemistry is shown in the product because there are no stereocenters present in the compound. However, it is important to note that the formation of a carbocation intermediate in the reaction allows for the addition of the electrophile to the nucleophile to occur from either the top or bottom of the planar carbocation. So this reaction mechanism can result in racemic mixtures of product if enantiomers of that product can be formed.